So, good day students, and welcome to the homework session following the first nugget in this lesson dealing with biofuels and the conversion of biomass to biofuel. In the theory session, we went through in some detail how the heating value is determined and how the energy density connects into the heating value. And what we shall do now is we will take a slightly different view on the heating value so as to connect it in a very general way to upgrading processes. And then we will talk a little bit about fuel quality in a general context. The aims, the intended learning outcomes from this nugget are what you see in this slide. So you shall be able to discuss heating value and heating density as two aspects of fuel quality. And you shall be able to adapt a critical eye to fuel conversion processes. To do that, you will have to go through the 3 appendices to the Busy Plan Handbook in some detail. And you will also have to study in detail the 7 introductory sections in the Busy Plan Handbook, Chapter 4.0. Let us now have a look at the heating value from a slightly different point of view. We now limit ourselves to look only at the effective lower heating value, because that is the energy that can be used in most practical cases. So we consider the fuel to be composed of 3 parts: combustible, dry and ash-free substance, water and ash. You will understand from the appendices that the fraction of ash on a wet basis becomes the dry basis mass fraction multiplied by 1 minus the fraction of water. And then the sum of the 3 weight fractions on a wet basis is unity. So with a total amount of m sub f kilos of wet fuel, we will find that the total amount of energy is the energy supplied by the combustible substance subtracted by the energy to boil off the water. So for 1 kilo of wet fuel we have this. For the following analysis and reasoning, we will use a different form of this equation, namely the one in the middle of this slide. And we will use that to look at what happens to the heating value as biomass undergoes a conversion process. First, we look at a simple drying process. So what happens is then that the mass of water in the fuel is decreased and the heating value increases. This is a positive thing, an improvement, and the ash content per energy unit will decrease, which is also a positive thing. But the ash fraction on a wet basis will increase. Compaction, like pelletization, changes nothing except the density. So all chemical properties of the fuel remain constant. The same thing goes for grinding to a fine powder aimed for pulverized fuel firing. Pelletization will increase the bulk density, while milling will decrease the bulk density. But none of them will alter the composition of the material. So all chemical properties of the material, expressed per mass unit, will remain constant. But physical properties like repose angles or bulk density will change. These things will have a significant influence on the handling properties of the material and on the transport and logistic costs. Pyrolysis is a conversion process with many phases. There is flash pyrolysis, high temperature pyrolysis, pressurized pyrolysis, and a lot of other process variations depending on what you're after. But right now we limit ourselves to a slow and low temperature, typically some 200 to 300 degrees Celsius, atmospheric pressure process. And this process is called torrefaction. What happens in this process is of course that the material is dried. So the water disappears. The temperature is so low that none, or at least only a negligible part, of the ash is gasified and disappears. But what does happen is that light hydrocarbon gas, volatiles of mainly low molecular weight, will form and leave the material. These light hydrocarbons will generally have high heating values, say 35 to 40 megajoules per kilo. But they will be diluted with other gases such as ammonia, acetic acid and such, which are also formed so as to reduce the mean heating value of the gases given off to maybe 15 to 25 megajoules per kilo. There will also be some heavier hydrocarbons called tar that will form and leave the material as a thermal cracking product. But part of this tar, and part of the lighter gases too, will react with a charcoal matrix on its way out through the pores. And this will hold some of the heavier hydrocarbons back so that they stay in the solid phase. This will change the composition of the dry and ash-free substance. It becomes enriched with respect to heavy and high heating value hydrocarbons. So the heating value of the dry and ash-free substance is increased, but at the same time is there a mass loss from the dry and ash-free substance. So the total amount of energy in the solid material will decrease. The householding of this energy loss is typically managed so that the heat needed for the pyrolysis process is supplied by the combustion of the light hydrocarbon gas mix mentioned earlier. So then are the total energy losses kept under control, but they are not eliminated. So for low ash fuels such as wood, will generally speaking the heating value increase through torrefaction. But for some high ash fuels, such as rice husk, where the ash content may be in excess of 40% on a dry basis, may the result be the opposite. In gasification processes is the picture further complicated. The idea with gasification is to partly combust the combustible substance and also to change the solid residue, the char, into combustible gases. For this, there is a need of an oxygen addition. Depending on the process, can this be done using air, and that is what I assume in this discussion. So the total mass of the product gas, supposing a perfect gasification, would be the incoming mass of the combustible substance, including the water, plus the total amount of air added. And the total outgoing energy will be the chemically bound energy in the product gas plus the sensible energy in the hot product gas. In general, the heating value is restricted to the chemically bound energy, that is, the energy that can be released through combustion. So the heating value will be the incoming energy with the combustible solids, and then that value is reduced by the sensible heat in the hot gas and with any energy left in the solid residual char. So the heating value in the gas is per definition lower in the outgoing gas than in the solid biomass. If the gas is cooled, then is the total energy in the gas reduced by the sensible energy, and the total mass may be reduced by condensation of the water. But generally speaking, will still the heating value be lower in the product gas than in the incoming biomass? But even so, may well the gas be a better fuel than the solid biomass. It may, for example, be simpler to use in a specific process. It is easier to run a glass melting furnace using a gaseous fuel than a pulverized fuel, just to mention one example. But then, to mention another example, may the ash content in the gas be enough to prohibit the use of a gas in a gas turbine? So just gasifying solid biomass does not necessarily mean that the new gaseous fuel is free of ash. The gas heating value can be changed by using oxygen gas instead of air as oxidizing medium. So, very simplified, we can say that there are three general gasification technologies. Low heating value gasification using air as an oxidizing agent. Medium heating value gasification using oxygen-enriched air. and then high heating value gasification using pure oxygen and maybe also water vapor as oxidizer. But the thing is, and what I want to demonstrate with this example, is that fuel quality is not something uniquely defined and easily determined. It must be understood that the conversion processes are not always and per se the same as upgrading processes, as it comes to the heating value. Sometimes other qualities are more important. The schematic in this slide is a copy of Figure 3 from the Unified Bioenergy Terminology Handbook. What you will notice from this schematic is that there are many different ways to go from the raw biomass into a biofuel. The choice of process is to a great extent determined by the properties of the biomass itself. But it must also be remembered that the raw biomass is often a biofuel in its own right. So you may not have to use any conversion process at all to introduce bioenergy into your local, regional or national energy system. And if you have to introduce a conversion of some kind, you must be well aware that not all conversions are quality improvements. A change of quality means that you adapt the biomass to a specific market. But maybe there was already a market for the unconverted biomass. Now it is time for you to set to work. Select 2 different fuel-based industrial sectors in your own region or country. Then go to the web page bioenergyprof.eu. Go on to the menu item Basics. Scroll down to find the link to the ResChains project. And then use this training matrix to find suitable biomasses and conversion routes to try to supply the industrial processes that you have selected. Once you have identified biomass qualities that may be used, then try to find out how much of these biomasses are available in your own region or country. The limitations to which fuels and conversions may fit which processes are to a great extent set by the heating value and the attainable combustion temperature. So once you have suggested a biofuel to use, then try to find the heating value of that fuel and compare to the fuel that is actually used in the industrial process. Play around in the training matrix and test different combinations so as to have an idea of the connections between end user and energy source via conversion routes.